All right, welcome to Chapter 9. This starts off with sequences, and that's part of a larger chapter. Sequences, something called mathematical induction, which we're not covering, and the binomial theorem. So sequences and the binomial theorem are what we're after from Chapter 9. And what is a sequence? Well, a sequence is a list of numbers, an ordered list of numbers, and the page that has the best examples of that is this list, this page here. So the sequence itself is this list, and by the way, sometimes when you want to talk about the sequence, we'll put braces around it. That really shouldn't make a difference. I don't think there's any question where you need to put in the braces, but the braces just mean we're talking about the sequence as a whole. But if we're just talking about the pattern itself, the braces might not be present like they are in this particular problem. All right, so we have this list, whichever list it is. We'll look at this one. And one of the things we want to do is figure out the formula, the algebraic formula for that list. A couple of assumptions that we're making, and one of them is n is the variable, so we use a sub n to talk about the function. We don't use f of x like we would in other chapters. We're using n as the variable. And, you know, if this was written in the more dominant, I was going to say traditional, more dominant manner of f and x as the functions, I'd write it this way. I don't want to say traditional because lists of numbers precede algebraic notation by probably 1,500 years. So if anything's traditional in terms of mathematics, it would be the idea of making a list of numbers. But function notation and functional equations have dominated mathematics for the last 300-400 years. But prior to that, this is what people do. And actually, the human mind is very good at one part of this list. Just got to say, we're really good at lists, really good at patterns. I even say that we find patterns where they don't exist. Like, who looks at the stars and sees a lion or something, right? We see something, we make a pattern out of it. Well, that's what we do. So if I look at this list, one of the things that most students are pretty good at is telling me what the next term is. They'll say, oh, look, you're multiplying by 3, so the next term must be 81. We don't have any questions about that, by the way. But noticing the pattern is okay, but what we're really looking for is the formula. So back to this. If you had this pattern, 1, 3, 9, 27, would you be able to find this formula? The formula is based on this idea that we're looking for what I call the invisible 1, that a formula where there's an invisible 1 in the first term, an invisible 2 in the second, an invisible 3, an invisible 4. Our job is to make those numbers visible. And what I mean by that is we need to visualize, hopefully, that 1, well, we recognize 3 is a key player in this. So, and I could maybe, my reasoning might go like this. 1 is 3 to the 0. 3 is 3 to the 1. 9 is 3 squared, 3 cubed. So I still haven't exposed a 1, 2, 3, 4 where I needed them, but if I work with it a little bit, 1 minus 1, 3 to the 2 minus 1, 3 to the 3 minus 1, 3 to the 4 minus 1. And if I do that, I've exposed the pattern, the 1, 2, 3, 4, and hopefully I'd see that it is 3 to the n minus 1 for any value. Even the one that we gleaned from this one, 81 is the 5th term in the list, and it's also 3 to the 5 minus 1. Now, we only have to do this a few times, this, I don't know, groping for a formula, because we will learn other formulas very shortly on how to do this. But this one might be a little easier to see. 1 over 2, 1 over 4, 1 over 8, 1 over 16. Hopefully you recognize the 2 to the 1, 2 to the 2, 2 to the 3, 2 to the 4. And so we can put that into a formula. I covered this one up. We'll erase it in a second, but remember, I'm looking for a formula that's going to give me, in this case, 3, 5, 7, and 9. We know the next few numbers, 11, 13. In other words, we're very familiar with this pattern. And you're not allowed just to say, oh, it's a pattern of odd numbers greater than 1 or something like that. I mean, you could think that, but thinking that way doesn't give you the formula. The most important thing is to look for a formula that works for all of these, that when you put in a 1, you get the first term. When you put in a 2, you get the next term. Second term. When you put in a 3, you get the third term. All right. So a couple of things on this one. There is a pattern that we all know. 2, 4, 6, 8, 10, 12. You've probably known that pattern since you were 4, 5, or 6. And the way I would describe this pattern using our notation, it's not the one we want, but it's pretty close, right? It's off by 1 every time. I describe that as 2n. It's 2 times 1, 2 times 2, 2 times 3, 2 times 4. So whatever n is, I'm just multiplying it by 2. So this pattern you've known for a very long time, 2, 4, 6, 8, 10, is just 2n. So this pattern, where it's 3, 5, 7, 9, 11, 13, is, no surprise, 2n plus 1. I just add 1 to this pattern that I've known, since I learned how to count. All right, this one's a little more involved. It's 1, 8, 27, 64. Hopefully you recognize the cubes. 1 cubed, 2 cubed, 3 cubed, 4 cubed, 5 cubed. Yep. The formula is n cubed. And then this would probably not be intuitive for most of us, but it's something you need to learn, and that is minus 1 to the n and minus 1 to the n plus 1 are these numbers things we put in front of the pattern, the early stage of the pattern, to indicate that the signs are changing. So if you see the sign go from start negative, then positive, then negative, then positive, if it switches like that, that would be minus 1 to the n. If it starts positive, then negative, then positive, then negative, we just put this in it. Try not to be extra clever by coming up with your own formula. We don't try to absorb this into the formula in any way. We like to have it as a separate factor. So leave it in your answer. So I haven't even thought about the 2, 4, 6, 8 yet. Just notice the signs, and we take care of the signs. When n equals 1, I get negative 1 squared, which is positive. You get the idea. Also, don't look for or don't try a different pattern like n minus 1 or n plus 7 or whatever. I mean, there are other things that might work, but the only two we use just by agreement are minus 1 to the n, minus 1 to the n plus 1. All right. Still need to figure out the pattern, but we already know this one. 2, 4, 6, 8. 2, 4, 6, 8. Yep. The pattern is 2n. So again, we like to have the minus 1 to the n or minus 1 to the n plus 1 first, and then the rest of the pattern follows, and we try not to manipulate that. In other words, we don't want to hide this by putting it somewhere else. Just like to lead with it, I guess. All right, so with that, let's look at an earlier example of how some of these look. Yeah. So you're going to see problems a lot like this, where they just give you b to the n equals, and they give you the formula. And they'll ask you to find a certain number of terms. They might ask you to find a random term, like the 30th or the 100th. But you have the formula. So that's the idea. Can you resurrect the list or resurrect the sequence or find the sequence just by having the formula? And you certainly can. So the first term, if the sequence is named B, is B sub 1. And so all the n's are going to be replaced. Well, if there's more than one, usually there's only one n, but if there's more than one n, replace them all with ones. So the author did that in red here. Replace those with ones. And if you run the calculation, you get negative 1/2. Now at some point, we're actually going to see the pattern. And so sometimes just using the pattern takes over, and that's kind of what the author did here. We calculate B2, and we get 1. So let me keep a running total here. Negative 1/2, positive 1. Put in B sub 3, and we get negative 3/2. And at least the author, anyhow, seems to think that from here on out, we don't need to calculate anymore. We can just embrace the pattern. So the pattern seems to be that the sign changes, and we're increasing by 1/2. So the next number would be 2. If we increase 2 by 1/2, that's 2.5 or 5/2, and the sign's going to change. Minus 5/2. And there's really no reason not to use the formula. I mean, we could certainly use the formula, but the idea is, what are humans better at? And the thing that people are very good at is, in general, extending a list. So if you have the list already going, and you can extend it by just maybe glancing at this, that works too. This is very unusual that they decided to graph these, plot these on a grid, but they plotted it. And of course, you notice what happens if you have an even number. The calculation's positive because -1 to an even number. And if you have an odd number, the calculations are negative. Not too surprising, but they're just plotting it. Notice this is the n-axis, and this would be the a sub n axis, or in this case, the b sub n axis. So we don't talk in terms of x and y anymore. We're talking in terms of b being the name of the function in this case, and n is the input variable. All right. Well, the next important thing about this, they introduced the factorial symbol, which is one of the buttons on your calculator that we're going to use in this next few sections. But you definitely want to be familiar with factorial. So the way factorial works, and they have it written this way, which is generally true. If n is greater than or equal to 2, n factorial, and let me just pick a number here that's a little bigger so you can see it. Let's do 4 factorial. So it's 4 with an exclamation point. We write it this way. I mentioned it's a calculator button. Some of your calculators, the button's a little hard to find. But it's a factorial button. Look like this, or maybe X with an exclamation point, but know how to find it. All right, so 4 factorial means 4 times 3 times 2. Now, they never stop at 2. They always seem to tack on this 1. I'm not sure what difference that 1 makes in the multiplication, but they always seem to put it there. In other words, you could leave it off and still the same multiplication. But there it is. 4 factorial means 4 times 3 times 2. That'd be 12 times 2. That's 24. And you could run that through your calculator and get that same value. A couple of interesting things, though, and that is 1 factorial is 1, and I suppose that makes sense. 1 factorial equals 1. But this one, it feels a little unusual. What's 0 factorial? Well, 0 factorial actually works its way into a lot of formulas. In other words, if you just apply a formula or apply a pattern or just apply some logic, sometimes you'll get 0 somewhere in the numerator or denominator of a formula or a fraction, and nature tells us it equals 1. I have to tell you that this is more of a definition than a calculation. And if I say it that way, it's a definition, not a calculation, I think students accept it a little bit more. The example I like to use in a class is, if I tap on a table and say this is called a table, you can't really ask me why it's called a table. It's called a table because it meets the definition of a table. It's a word. It's a definition. So 0 factorial equals 1 is a definition. It's by agreement, but it's by agreement for serious and good reasons. So be careful with this. This might trip you up a few times. You have to learn that 0 factorial equals 1. All right, so the factorial symbol can work its way into a sequence. I'll do that somewhere. Let's make one up here. So let's say I had a sequence that I called a sub n equals n plus 1 over n factorial. What would that list? What list would that give me? Well, it would give me 1 plus 1 over 1 factorial, comma, 2 plus 1 over 2 factorial, 3 plus 1 over 3 factorial, 4 plus 1 over 4 factorial. You get the idea. I could calculate each of those, but just be prepared for factorial to be in a formula, a list, or something like that. All right, in an effort to keep these videos a little bit short, I'm going to start another video on this section, but this is section 9.1, part 1.